Hi, I suppose it's time for another one of these, and what we're going to look at today is light and colour. And it's trickier than it seems, but it's also simpler than it seems. And if we get it right the first time, it should be fine. So without going into too much depth, let's look at what happens when we find out about light and colour. All right, light. We could write a book about this stuff, but let's just work out some basics with it. It's part of a big group of radiation, and that's called collectively the electromagnetic spectrum. But one very tiny part of the electromagnetic spectrum, or EM radiation if you like, is light itself. And by saying it's only a very small part, it is only a very small part. Now we're only concerned with the part that can be detected with our eyes, and that's the big thing about light, sometimes called white light, but that's another story, and we'll get into a little bit of this. You won't be tested on electromagnetic radiation, you won't be tested on a lot of things, but your understanding of colour is important because, as we know, plants are green. Now, one of the things we can say is that a light carries energy. And the funny thing is, the amount of energy it carries will depend a lot on the light itself. And the part that we can look at for that is the colour. Now, we're all conversant with the idea of a rainbow, where we've got the colours red, orange, yellow, green, blue, and then we have two very interesting colours, I for indigo and V for violet. Now indigo's a blue-purple, and believe it or not, we used to have an ink we used to write with, and in the old days the ink was called indigo ink, and we can still have that on your art lessons perhaps, I don't know, but I know when I was at school we had indigo ink in our art lessons. It was one of the nice colours we had. And then of course there's violet, and violet is a very deep colour, and it's almost a purple colour. So while we're going through these, we know that this one carries the most energy, and this one carries less energy. Not the least, but less. So red is the least energy, and violet is the most energy. Now with light, the next section to the violet energy is something we might have heard of, and I'll just use a different colour for this because I think it's quite important. You might have heard of this stuff, ultraviolet, which means even more, it's going to have a different properties of violet, but we can't see it. And it also comes from the sun and various other bodies, and as we know, it can be linked with skin cancers and goodness knows what. But that is here, so it would carry even more energy than the violet. Now, if we then move on with this, it's been known for a long time that when a rainbow forms, what actually happens is we get light coming from the sun, and when it goes through water droplets in the air, water droplets converts it from the light from the sun, which we call white light, into the colours of the rainbow. And as before, red, orange, yellow, green, blue, indigo and violet. Roy G. Biv, as some people might have said, and you might have seen this used to describe it. Roy G. Biv. And that describes the colours. Now if we look at it, we can see that red is always on the outside, and we can see the purpley colour. We should be able to see the differences as we go through. We can see the red, they sort of become a bit indistinct. There's a bit of orangey, then into yellow, then into green, then there's a bit of blue, and then there's a violet. And this happens in our skies with the rain, as I said, anytime we have this, if you have a sprinkler working with it, it also works. You can have a rainbow forming when you just have the hose and a sprinkler working. The same idea applies. You're simply allowing the light from the sun to release, if you like, or to show you what it's actually made of. So when we thought light from the sun was just a same all the way through, this shows us that it's actually different. So this looking the same, but something as simple as a water droplet, or some people might have crystals on their windows or little things which break light into the spectrum itself. That's how you get the little dancing spectrum through your bedroom or through in a room in your house. We can see that light is actually made of these 7 colours that can be detected by our eyes. Now, another way we can do this is to filter light. And when you filter, normally we say you take something out and let some things go through. So a filter is something, it's like, I thought this was a very, very good analogy. It's like a door. It will let certain things through and other things that you shall not pass. So it absorbs them or holds them in. Now the colour of the filter is the colour of the light that goes through them. So, for example, if we have light from the sun over here and we put a blue filter, then what it does, the door stops red, orange, yellow and green and indigo and violet, but allows the blue to go through. Alright, so the colour of the filter decides what colour light comes through. Similarly, if we have a red filter on, the orange, yellow, green, blue, indigo and violet will not get through, but red will. Alright, so the filter colour decides which colour light comes through. And it's really amazing that our atmosphere is a filter. And it is a blue filter, so it lets blue light through. These bluey colours, it lets them through a lot more than the red ones on the way through. And it's very interesting also when we look at our water. If you've ever been snorkeling or scuba diving, you'll know that after around about 10 metres of water, the only light that comes through is the blue light. So seeing colours like red and orange, you don't see them anymore because of its filtering effect. Most of the normal colours we see though, we have chemicals in, and they're normally called dyes, right? And the dyes are pigments, and pigments are things like, as we know, we've got chlorophyll, which is a pigment. So dyes and pigments, they will either absorb the colour or let it come out of them. So let's imagine we have this situation across here, where we have someone who has a red shirt and a blue pair of shorts on. They are being white light from the sun with all of its colours comes in and hits those dyes that are in the clothes. Now in the case of the shirt, what actually happens is the colours of orange, yellow, green, blue, indigo and violet are absorbed by the dyes in the shirt. And the only colour that comes back off and is reflected to our eyes is red. Right? Now similarly, because the shorts have a different dye in them, right, it will absorb a red, orange, yellow, green, indigo and violet, and the blue will come off. So the blue is reflected to our eyes. So our eyes across here will only see the colours that are released by the, or reflected by the dye. All right. Now this is very, very similar to what goes on in plants. we've got, instead of that, if we've got our leaf, if we've got a lovely little leaf here, then all that happens is all of the colours of the spectrum come in. So our light comes in, but the only colour that comes out is green. So all the other colours, the red, the orange, the yellow, the blue, the indigo and the violet, are taken in by this chlorophyll. And the green light that is left over or is not absorbed by the chlorophyll comes to our eyes, and that's why we see green light. Now, one more thing about light, and in plants, is we tend to find that there are partners or complementary colours. So if we want to find out more about something and what they're doing, we look for the other end of the spectrum. And you can see we've got a colour wheel, and we've got complementary colours that are with them. So, for example, if I am green, or if my clothes are green, then they will be absorbing that colour, the red colour. If my clothes are blue, they're going to definitely be absorbing the orange colour. And so this is how we can decide what colour to actually use to study objects. So if we are looking at a green leaf or a green chemical like chlorophyll, our best way of studying it would be using the complementary colour of red. Alright, so chlorophyll, if we're doing it, it would be best to be looking at red light going into it and see what happens. And on that note, I'm going to stop.